Okay, what's left in chapter 7 is to prove the channel coding theorem. This is the most beautiful part in the information theory. So it is long, very long. The proof is very long and difficult, but it is worth to study the proof. So by studying the proof, we know what a channel code is, how to construct a channel code, and by studying the proof techniques, we can utilize all the materials that we have studied before the midterms. For example, convergence in probability, using the typical sets. Convergence convergence occurs when you increase the size of the dimension. All these ideas put together, we can do the proof of channel coding theorem. So we will do that in the next lecture. In this lecture, I want to give the sketch of channel coding theorem, a sketch of the proof of channel coding theorem. So it gives you an idea why the mutual information becomes relevant. So let's consider the first item. Recall the typical set argument. We talked about typical set, epsilon, and the length n. So typical set has to do with the length of the sequence. In this case, the length of code word, and typical set argument involves epsilon, a small number. So the convergence in probability says for epsilon, any epsilon greater than 0, the probability of a typical set. So the probability of a sequence, let's say y belongs to, or x belongs to this typical set, approaches 1, right? Approaches 1 as n goes to infinity. So that is the key idea, convergence in probability idea of the typical set. And another item was the typical set is a collection of all x where the sample entropy and the true entropy, the difference between the two, is smaller than epsilon. We can write the typical set this way, right? And then probability of such a set, probability of any x belongs to, so x from the random experiment belongs to the typical set, goes to 1 as n goes to infinity, okay? Or we can say that this probability is greater than or equal to or minus epsilon as n goes to infinity. It has the same meaning, okay? So that's the convergence in probability. That is the definition of a typical set, and so on. So the argument is when you select an x, vector x, randomly, that vector x belongs to this typical set, right? Typically, right? So probability of such event is close to 1. That's what it means, okay? So probably that x is not equal to the typical set approaches to 0. So that's what it is, okay? Now apply this to the random variable y, conditioned upon an input. So here in this case, fix a sequence x and consider collection of output sequence y's. In this case, we can talk about typical sets on y, and then we can define typical sets on y, and then typical sets based on conditional distribution when x, so probably I need to write one more time, okay? So in this case, we can talk about typical set this way, is defined to be collection of all y's, sample entropy minus entropy on y, given x is equal to that small sequence, that small x, a particular x, particular vector you select, and then when you do random experiment, these are the possible set of outcomes. That's what we mean by the typical set in this particular problem. So given x, because of the channel noise, there are certain set of outcomes of y typically occurs. That's what this means. And that y belongs to this typical set is the this argument that we can say that y, you select any y, and then that becomes that belongs to this typical set defined right here, and then probability of such event goes to converges to 1 as n increases to infinity. So that is what it is. And then this occurs with for any epsilon greater than 0. So for any epsilon greater than 0, this occurs. That's the application of a typical set argument we learned in chapter 3 to the channel coding theorem. So this is what it means. And the size of this typical set is equal to this 2 to the power of n, 2 to the power of entropy. So this is the entropy, the uncertainty on y for a fixed x. So this has to be actually equal to that small, let's say x1. So 2 to the power of n h y of x is equal to a certain fixed fixed one. Okay, so but we can use the average ones. So basically, for each input, the channel give you some symmetric distribution on the output. So we can assume that each one of these, output distributions for fixed x are the same as we have seen in the symmetric channel. So we can just ignore this part, and then we can just close it right there. So for each input, we have a fan out of output, and then the output belongs to within this set with a probability very close to 1. And then with this sending x2, the output is output belongs to the fan out of this x2. Okay, and another x, let's say xn, let's say m, and then fan out like that. And as we have seen in noisy typewriting writer problem, if we have x1 and x2 selected closely, they both of these fans overlap with each other. In such a case, it is difficult to distinguish what was the input given the output, right? Because we have overlaps. But if we disallow overlap of these output balls, so if output balls are not overlapping with each other, and we selected input in such a manner that the overlaps at the output space do not occur, then we can utilize the idea of noisy typewriter problem to have the maximum number of input symbols utilized, right? In such a case, we can obtain the capacity over the noisy typewriter problem. So we have done that, right? Instead of using all 26 letters, we select the input to be far apart so that the overlap doesn't occur at the output space. That's what we have done, right? We call that. So instead of A, B, C, all of them using, if we don't use B, overlap does not occur, and then given the output, we can we can perfectly determine what was the input, right? So instead, just to imagine more complex version of noisy typewriter problem. So given the input, you have a fan out of outputs. Given the input, you have fan out of output. If we select the input in such a manner, those fans of output do not overlap with each other, then we don't make decision errors, right? So we can, for example, if we receive Y belonging to this fan, then we can say X1 was the input. If we have output belong to this fan, we can say that X2 was the input, and so on and so on. So in terms of capacity, which is the maximum number of inputs that we can select to carry the information, can be described by number of balls we can pack inside this output space. The size then we need to know what is the size of the output space. That can be described by typical set argument, which is 2 to the power of NHY. So there are this many sequence of outputs with a length n. And then among them, we have typical sets based on the conditional entropy, h of y given x. So that's the size of smaller ball, which is this, and then the number of smaller balls that can be packed inside this bigger ball is going to be the number of input sequences that we can select at the input space. Okay, so that will determine the capacity. So the number of input that we can select at the input is going to be determined by total volume of the output space, which is 2 to the power of NHY. Right? That's the total number of sequences of length n typically occur at the output space, and divide that by the volume of the smaller ball. The volume of smaller ball is 2 to the power of n times this. Okay, so total volume divided by the volume of the smaller ball. Well, the size of the typical set of the output space divided by size of the typical set for the conditional. So that's the ratio. That is the number of inputs that are distinguishable. So these are the number of inputs that are distinguishable at the output space. So no overlap does not occur. So actually, this is the maximum number of input, right? You can certainly choose only, the balls very far apart with each other. Then the number of number of inputs that you can use is going to be smaller than this maximum number. But what we want to know is the maximum possible inputs so that they are distinguishable at the output. Okay, so in such a case, this one will this ratio will give you an idea of capacity. So this one is nothing but the same as this one right here. The ratio of these two numbers is just written this way, and then we notice that it is equal to, this one is equal to the mutual information between the two, and this ratio is nothing but 2 to the power of n times mutual information. So this is the capacity. So maximum of this is the capacity of the channel that is given. So the channel gives you the fan-out effect. If the channel is very noisy, the fan will be larger, then the number of distinguishable inputs that you can select is going to be smaller because the smaller ball has gotten bigger. But if the fan-out effect is smaller, right? Smaller, if this becomes smaller because it is less noisy, then you can have many balls, smaller balls packed inside this typical set of outputs. In such a case, the capacity can be increased. So how noisy the channel is will determine the capacity of the channel. And whenever you select the number of inputs that is smaller than the capacity, the probability of decision errors will get very small. Okay, so that's the key idea of channel coding theorems. It uses typical set argument, and we can utilize the intuition that we developed in the noisy typewriter problem. And we know what the consequence of selecting large n, right? So we can select a smaller epsilon if we have large n. And basically, that's the key idea explained. Okay, so we will use this key idea to the proof of a channel coding theorem. Okay, having said that, I will conclude this part of the lecture.